Okay, so what is the relativistic slide rule? Okay, so this is it here at a velocity of 0.6 c, and you can see how it changes. Velocity goes up to the speed of light and then dropping to 0. Okay, so that's how I discovered all of these lengths. It's the only way to discover them is by discovering this geometry, right? But having done that, I then wanted to look at it in other ways. So what I did was I decided to graph all of these changing connections as functions, and then I found that as I changed my velocity, I can just read off the value of the function, kind of like taking the derivative. Okay, so the functions are integrals at all velocities, so you can see how they changing relative to each other at changing velocities. But if you want to read off their actual values at a specific velocity, for example 0.6, then I can read off a value, for example at 0.6. The phase velocity is 0.75, spacetime is 1.066, length contraction 0.8. You can just look at all these things, they're all getting read off. And now I was having trouble with Desmos, wasn't able to handle the creating all those functions, so I just took a photograph, because they don't change anyway, because they're integrals, they're just frozen in time, you could say, anyway. Okay, so that's what it looks like when x is 1 over t, when I make x 1 over t. But you can also make x equal to L over t, which is b, and then all that happens is the thing sort of gets squashed so that x doesn't go above 1. You still get the same derivatives, but you have to remember that you're talking about x being L over t. So let's go to what that looks like now. So here it is again, just a quarter of it, the top right hand quarter of it, but it's all squashed down. So now let's look at a velocity of I'll say 0.6 again, I guess. And again, you can just read off values. Yeah, that's velocity L over t, and various other ones. There's that space-time. Where's gamma? There's gamma there, 1.25 at a velocity of 0.6. So you can see it's squashed. So that's another way of looking at it. And then I like this way of looking at it, which is to take the natural log, and then let's just get rid of that first, and get rid of that. Keep that. Get rid of that. We're not interested in that yet. Okay, so now you can see how they change with velocity relative to each other. See all the yellow quantities are heading towards 1. All the green quantities, they were all heading up, and they just started falling again. They go from 0, start heading up to a maximum of 0.5, one of them, and then just start dropping again. All the green values, there's 9 of those, 9 well-known ones anyway. You can see as velocity increases, time squared, space-time, inductance and time, they all drop to 0 from infinity. And then other quantities, you can see as the velocity increases, you can see resistance drops, permeability drops to 1, whereas the cosmological constant in gamma increases to infinity from 1. All these purple quantities, as the velocity increases, they've gone from 0 and they just go up to infinity, all the purple ones. Length, that's blue. Area and volume, they're blue. As the velocity increases, length contraction increases, so they just drop to 0 from 1. But they're all doing slightly different things. Some key points, they have the same, a lot of coinciding values. For example, square root of 0.5, you've actually, a lot of them have got the same values, so you end up 1, 2, 3, 4, 5, 6, 7, 8. You've only got 8 different values, and there's no convergence or divergence either. So that's an interesting one. Also the golden ratio is another interesting one. You see, you drop down to about 14 different values. A lot of them are the same. So that's what's special about the golden ratio. And probably all I want to say. The green quantities are going to turn out to be conserved quantities. You got momentum, linear momentum, angular momentum, and energy, which are all conserved quantities. And then as the gauge changes, you find the force increases. Anyway, I can't just explain everything in the one go. Yes. Yeah, okay, that'll do. Maybe I'll include this one in the video so you can play with this one. Yeah. Right.